Hello everyone, I am Vishisht Priyadarshi. Today I am going to talk about segmentation and paging in Windows XP. So segmentation and paging are two different non-contiguous memory allocation schemes that is used by operating system. In segmentation, the code is divided into variable sized sections which are known as segments, while in paging the program is divided into fixed sizes called pages or page size. So in segmentation, we provide a mechanism to isolate those segments which are known as code segment, data segment, and others like stacks. And they run on the same processor without interfering with one another. They are kind of independent with respect to each other. While in paging, we provide a mechanism for implementing a conventional demand page virtual memory system where sections of a program's execution environment is mapped into physical memory as needed. So the type of memory management scheme that we will going to use will very much depend on the underlying instruction set architecture that is supported by the operating system. Windows XP support these three platforms, but we are going to focus on the first two, that is IA32 and x86-64. On a side note, IA32 combines both segmentation and paging, but segmentation is generally disabled on the second one, which is 64-bit mode. So under segmentation, all the segments in a system are located in the processor's linear address space. And to locate a particular byte in a particular segment, a logical address is generated. This logical address consists of two parts, the first being the segment selector and the second being the offset. Segment selector is nothing but a 16-bit identifier for a segment. It does not point to the exact location of the segment, but it helps in generating that segment using what is known as segment descriptor. This segment descriptor consists this segment selector consists of three things. First is the index, the second is the table indicator flag, and the third one is the RPL. So index is nothing but the index. Table indicator flag helps us in knowing whether it is a GDT or a LDT, that is global or local descriptor table. The third one, RPL, requested privilege level, tells the privilege level of this segment. It varies from 0 to 3, the 0 being the most privileged level. And the second part is the offset, which is the offset part of the logical address, which is then added to the base address for the segment to locate a particular byte within the segment. So now we'll talk about segment descriptor tables. A segment descriptor table is nothing but an array of segment descriptor. It can be a variable in length, variable size and length, but it can contain only up to 2 to the power 13 byte registers. There are two types of descriptor tables present in Windows XP, which is the first one known as global descriptor table. Global descriptor table contains all those segment information which is shared among all the processes. Since it is a global, so each system must have at least one GDT defined. And since GDT is in this array, so it must have some location where we can access it. So that particular location, which is its base linear address, is stored in the GDTR register. Now talking about the local descriptor table LDT, it is local to a processor, and each processor which performs some different tasks can have their own LDT defined. So there can be multiple LDTs in a system. On the right hand side, as we can see that this is the entry of a descriptor table which is used by Windows XP. Now we'll talk about GDT and LDT. As mentioned earlier, the processor locates the GDT using the GDTR register. The same is the case for LDTR register. Now, the LDT is located in a set system as a segment inside the GDT itself. That is, the GDT must contain a segment descriptor for the LDT segment. If the system supports multiple LDTs, each must have a separate segment selector and segment descriptor in the GDT. And to eliminate the problem or the speed required for the address translation while accessing the LDTs, various attributes like segment selector, base linear address, and the access types of the LDT are stored itself in that LDTR register only. Now, talking about the particular entry and descriptor table, they contain some various flags like S flags, access flag, dirty flags. So S flag stands for whether this is a code segment or data segment. Dirty means whether we have modified this segment or not. Read write enable means whether it is a read only, write only. Same goes for code. and data, like when the segment is a code segment and or it is a data segment, those flags will be activated or it will be disabled. Segment registers. To reduce the address translation time, usually the processor provides registers for holding up to segment selectors. That is, we replace this business of doing the translation and adding it to the offset. We simply provide a set of segment registers which can be immediately looked up into by the operating system and corresponding information can be retrieved. Each of these segment registers support a specific kind of memory reference, which are code, stack, and data segment registers. These must be loaded for a program to run. Additionally, the processor provides data segment registers known as ES, FS, and GS, which can be used to make other data segments available to the currently executing program. To access a segment, a program must get to it via segment register. Usually the operating system can provide thousands of segment registers, but initially these six of them should be loaded into the memory for the immediate use. Now we will discuss about paging. Paging helps us in reducing the external fragmentation that is created by segmentation. It also deals away with the problem of variable size segments. So Windows XP combines both segmentation and XP as we can see in this diagram. So the linear address generated by segmentation now undergoes through the process of paging to locate the particular address in the physical memory. So to implement that, a physical memory is divided into fixed size frames which are 4 kilobyte on a 32-bit system. In XP, the virtual memory manager, that is VMM, maintains a two-level memory map in the system portion of each process virtual address space. So what it does, that linear address is divided into three groups, which refers to the page directory by the first 10 bits, next 10 bits by the page table, and the last 12 bits point to the particular offset into the physical page. We will discuss more about it in the upcoming slides. So as we saw that the top 10 bits of the linear address into a index into a page directory. This page directory is located in a particular location, and that particular location is pointed out by the control register CR3, also known as PDBR. This page directory is actually contains 1024 page directory entries, PDEs. Each PDE contains the base address of a partial page table which is indexed by the next 10 bits of the linear address. So each this contains the PT, which are the top 20 bits of the physical address. So how everything fits into the picture is described in the last point. So in the first stage, the address in the CR3 is concatenated by the top 10 bits to get us the location of a entry in page directory. Now we go on to that particular location, extract out that particular value from the PDE and concatenate it with the next 10 bits from the virtual address space. This combined address gives us the page table entry or PTE. Now this entry contains the page frame number corresponding to the page's location in the main memory. Now we'll take this page frame number and add page offset to it, and the whole thing that we get is now the physical address which can now be used to find out the exact location of the information which is stored in the physical memory. Table and prototype page tables. A page table is simply an array of 32-bit page specifiers. It is itself a page and therefore contains 4 KB of memory or at most 1K 32-bit entries. Two levels of tables are used to address a page of memory. At the higher level is the page directory, as we looked in the previous slides. The page directory address up to 1K page tables of the second level. A page table of the second level address up to 1K pages. So all the tables addressed by one page directory can address 1 million pages, which is 2 to the power 20. And now since each page contains 4 kilobytes of memory, the table of one page directory can span the entire physical address space, which is 2 to the power 32. The entries into the page table are known as page table entries and they have a specific format. One of the features of Windows XP, known as copy and write, makes use of a special type of page table known as a prototype page table. The PTE of a copy on write page does not point directly to the frame in which the page is stored. Instead, it points to a prototype page table entry, which is a 32-bit record that points to the location of the shared page. When a process modifies a page whose PTE protection bits indicate it is a copy on write page, the virtual memory manager copies the page to a new frame and sets the process PPTE to a reference the new location. All the other processes PPTs continue pointing to the original frame. This slide shows the structure of the page table entries. So it is a 32-bit identifier, a page table entry. So the first part contains of the page frame address, which specifies the physical starting address of a page. It is the address of the page frame that contains the desired memory operand. The rest of the part contains some bits like present bits, dirty bit, and some protection bits. So the present bits indicates whether we can use this page table or not, whether we can use this page table entry or not. If the present bit is set to be 0 and an attempt is made to use the particular page table entry, the processor signals a page exception. D stands for dirty bit and tells us about the page usage as I mentioned in the previous slides. The read-write bit and user-specified bit are not used for address translation, but they are for page-level protection, which the processor performs at the same time as address translation. This slide is the continuation of the previous slide, where here we have more elaborately explained about the page table entries. The first 4 bit determines the page file and the next 20 bits determines the offset in the page file. So that these 24 bits help us locating the data in the page file. Then we have 5 protection bits and 3 state bits, which are similar to what we have explained in the previous slides. Now XP allows the application to allocate large pages by making use of a TLB, translation look aside buffer. It is a very fast hardware cache which is used to store some of the pages which are referenced very quickly to reduce the translation time and increase the speed of the lookup. With this, we come to the conclusion of this presentation. As we have seen that Windows XP uses a combined segmentation and paging model. It has its own advantages, like segmentation has its own protection feature, while paging deals away with the problem of external fragmentation because of the fixed frame sizes. Despite this, in 64-bit Intel architectures, segmentation is generally disabled. It is only enabled in the beginning when the system is running in real mode. There are actually many different types of paging modes, but they too follow the similar structure as we have discussed earlier. Some of them are IA32-bit paging with 4 MB pages, PAE paging, which is physical address extension paging, IA32E paging with 4 KB pages. So as we see, these are the some of the paging models that we can use. So this was my presentation on segmentation and paging in Windows XP. Thank you.